So Lonnie's going to talk with us about rapid climate change in the Earth system, and he's going to talk about the past, the present, and hopefully the future. And then hopefully it's a hopeful future.
Thank you. I also want to point out that, as David Keeling was saying, all this wouldn't be possible if you didn't have your sponsors. And over the years, these are some of the organizations that have sponsored this research. And that's an extremely important part of this. Our international collaborators, Yao Tangdong and Vladimir Mikolenko, have played very important roles in this program. Now, I have a few objectives. I want to point out why the tropics are so important as recorders of climate and environment for the planet. Requirements for success in our perspective from our research at Ohio State. I would argue that glaciers are probably our most visible form of global warming. I mean, people can see this, and it's been documented around the world. We'll talk about some of the things we know with certainty from this work, things that on evidence seem probable, and then evidence for abrupt change in the past and present, and then time perspective for the current change. And I'll go through this fairly quickly. Take home up front, here's the photo that I took back in 1977 when we were just starting on this research. These are annual layers that you often get in the tropics because you have a very distinct wet and dry season. This photo on the right is actually the same place in 2002. So you can see that not only are we losing the glaciers, but we're also losing a very important archive of the climate of the past. The tropics are a very important part of the world because we have 50% of the surface area of the planet between 30 north, 30 south. And there are some big systems here, such as the hydrological cycle. This is where most of the water vapor is being pumped into the atmosphere. It's also something that you can actually see on any given day when you look at the Earth from space. You can see the intertropical convergence zone. You can see the zonal distribution of annual precipitation and the dry zones north and south of that. The other thing that makes the tropics, I think, really important on the issue of global warming is the temperature distributions. If you look at sea surface temperatures, as you see in this central panel, you can see there's quite a bit of variation. And if you look at precipitation around the Earth, you can actually see how that follows those SSTs. But when you get into the mid to upper troposphere in the tropics, you get a very uniform temperature. And that's where these glaciers are located. Now, this is the team that we have at Ohio State, and if you look at these folks, some of them you may recognize, but it's an international team at our laboratory, and I think to do this type of research, you really need to have that. The other thing is the laboratories themselves. We have Class 100 clean rooms in which the measurements are made for chemistry and dust. Isotope laboratories, extremely important. For our work, an archive, of course. When we started this, we had no idea how important this archive would become, but we have over 7,000 meters of core stored at minus 30 degrees C here. This is the only tropical archive of cores on Earth. And as we've come into the beginning of the 21st century, we have lots of people coming from labs around the world to collect samples from here. So it's become much more valuable than we thought, and as I will shortly show, the fact that we're losing these archives increases the value of having that. The other part that's given us success is in the drilling, the technology, being able to design and build our drills for the programs where we're working. To go above 20,000 feet is a hard job, but if you have to take 6 tons of equipment up there, it's even tougher. And so having that is extremely important. I would also say that there would not have been another time in our history that we could have done what we've been able to do, because we use technologies like Kevlar cables that have been invented in engineering. This is an electromechanical drill system that actually physically cuts the core. The geodesic dome that you see here was designed and built by a graduate student in mechanical engineering, and they build the structures and they get to go out in the field and actually test them out. In 1980s is when we really started working in the tropics, and the first ice core was recovered from the Quelccaya ice cap in 1983. And with a 20-year perspective, we were very fortunate to have chosen this ice field. Couldn't have known that at the time, but it's beautifully laminated, and it turned out that it's the largest tropical ice cap on Earth. And it provided a very fantastic annual record. In the 1990s, we started drilling some of the higher places like Huascaran, which is the highest tropical mountain on Earth. And here in the Mccaw, we found ice that goes back over 19,000 years. So you can look at isotopes and nitrates and chemistry from the tropics from this time. And if someone had said, would you be able to do that? I would have said no. A lot of, in science, it's by going out there and actually seeing what it provides. Then in the later in the 1990s, we worked with our Chinese colleagues over in the Himalayas and in Tibet, looking at monsoon and long-term monsoon climates in that part of the world. Now, one of the things that we've found as we've gone around to recover these cores, and all these dots are places where we've drilled, is collecting photographs of what's happening to the glaciers. Because I think this works much better in places like Washington, D.C. than things like isotopes. But I'm going to show some of these to you. This is the Mccaw Glacier up in the Brooks Ring, so very high northern latitude, 1958, and then 2003. If you go to the Muir Glacier in southeast Alaska, photo taken in 1941, compared to 2004 in August. This glacier was over 800 meters deep. And so you can look at how much ice is being lost from the land. And the retreat up this valley is about 15 kilometers. If you go to China, the glacier number 1 is an example of what's happening there. These two glaciers are joined in 1960. By 1990, they're separating. 2001, they've separated. The glaciers throughout the Himalayas and Tibet are behaving in this same fashion. Here in North America, Glacier National Park, Mccaw Glacier, 1910, and another photo taken in 1998. And if you look at Glacier National Park, the Boulder Glacier, 1932, people here for scale, and then in 1988. It's estimated by within 30 years there'll be no glaciers in Glacier National Park. If you go to the tip of South America, you can see a similar 1945, this glacier coming out of the Andes, and then by 1998, if you go north to the northern part of Patagonia, photo from 1896, and then a photo from 2001. So the loss of ice is very clearly taking place. Probably one of the most famous places is on Kilimanjaro, photo from 1912, which is the oldest photo we can find. This is actually glaciers coming down. Bruno Messerli took this photo in 1970. You can see a canyon starting to open at the top of the mountain. By 2000, when we drilled there, you can see how much ice has been lost. And if you go there today, this is what you'd see. This is a northern ice field in Furtwanger in the crater. But this is the largest ice body on the mountain. In 2000, we had aerial photographs flown so we could make a map. This shows the ice of the northern ice field, Furtwanger, and the southern ice field in 2000. And if you compare the amount of ice on the mountain in 2000, the white areas show that, and the oldest map was made in 1912, which is the lighter blue areas here. So you can look at what's happened since 1912, and there was 12.1 square kilometers in 1912. We're down to something less than 2.6 square kilometers today. So over 80% of the ice has disappeared. And if you look at all the maps in between and you kind of project this in the future, you see before 2020, if things stay as they have been since 1912, the glaciers will disappear. Now, since then, we have evidence of what's happening. This is what we think the last piece will look like. This is part of what was the eastern ice field. The ice walls up on the northern ice field, this is the largest thickness on the mountain. It's about 50 meters. We put in stakes here in 2000, and Doug Hardy and his team from the University of Massachusetts been measuring those. And this whole wall is retreating at about 0.9 meters per year. If you look at the stakes, we initially put up on the summit, and Doug Hardy's been measuring. This is in 2000. This is what it looked like in September 15th of 2004. And so we've lost 1.84 meters at this site from the surface down. This is solid ice that's we're losing from the mountain. And this has a big impact on our ability to study glaciers because we need a timeline with the present. And when we drilled the cores in the year 2000, we used the chlorine 36 spike from the Ivy test as a time marker. This has been annually dated in places like Huascaran, and here it is in Kilimanjaro. But it was 1.6 meters below the surface in 2000, so it would be gone at this time. So the ability to tie the top of the record. Here's a stake on Furtwanger, and these are what Doug has shown, the loss of ice from these stakes since 2000. And on the northern ice field, we're losing on average 1.5 meters. On the southern ice field, we've lost 3.5 meters of ice. And when you consider this Furtwanger is only 9.5 meters thick, it doesn't take much before these disappear. The other thing, of course, that's happening, if you look at the mountain itself, here in 2003 was the first documentation of a lake actually bursting out of the side of the Furtwanger Glacier, flowing across where these 10,000 tourists come up every year. And there's no written documentation of this water being present on the summit that we've been able to find. And ice is a threshold system. If it's -1 degrees, it's okay. But when it becomes 0 and it starts to melt, it takes about 7.5 times less energy to melt ice than to sublimate ice. And so I think that we may actually be passing a threshold on this mountain. Here's photos taken on July 2002 showing the lower section of the Barranco Glacier, the little Barranco Glacier. There's people. And these are the boulders. These are colored. Doug colored the same boulders so that you can look at September 2004. And you see how the ice is coming up from the bottom of the mountain. So not only is it not accumulating, we're losing it from the bottom up. But the real question we always have is, can you put it into a perspective? There's a really short time records, and you can use the ice cores to do that. One way, we have 3 cores that we drilled the bedrock from the northern ice field. It's just to look at the ice itself. When you have a glacier, snow falls, it gets compressed, it becomes ice. And when it does this, the bubbles are finely disseminated in the ice. And throughout the 50 meters of this core, this is what it looks like. Very fine grain. But in the very top, 65 centimeters, it looks like this. And you can see these elongated bubbles. They're 12 to 15 centimeters in length. They only occur when you have meltwater and you have refreezing. Now this record goes back 11,700 years. And that would suggest that this condition has not existed over that period of time. Otherwise, you could physically see it in the ice, in the preservation of the ice itself. If you look at the Andes in South America, this Quelcaya ice cap, which we've been studying for since 1974, actually. This is the outlet glacier, Coricalis, which is the largest outlet glacier. This is bedrock, and we set up a baseline up here in 1978. This is before global warming was an issue with anyone. And this is what this glacier looked like in 1978. Very healthy glacier, kind of convex. There's a little pond down there. Then by 2002, this is what it looked like. The lake covers 78 acres, and we've been able to map that and actually look at the rates of change of the retreat of the glacier. Here's 1978 coming up to 2002, and these are the margins, the terminus, going back to 1963 when the first aerial photographs were taken in this place. In this first period of measurement, the retreat is 4.7 meters per year. By 2000, coming up to 2002, it's up over 200 meters per year. So it's almost 40 times faster. And by 2004, this is what it looked like. The retreat's continuing. We took a sonar, sounded the lake. The lake is 60 meters or over 200 feet deep in the center part and didn't exist until 1991. So the changes are really dramatic. And if you look at what's happening to glaciers in the 20th century around the world, and the mountain glaciers, all these red areas are places where glaciers are retreating. There was this place up in Norway and Sweden, which up until recently was receiving more snowfall in the wintertime, and snows that used to come with storms into the Alps have this more northerly trek. Since 1999, these glaciers have also started to retreat. In 2004, there were 26 glaciers observed. Of those 26 glaciers, 24 had retreated more than 20 meters at the terminus in 2004. So even this area, which was one of the areas that some of the climate skeptics would point at, it seems to be behaving in the same fashion as other tropical mountain glaciers. So things we know with certainty: glaciers are disappearing, and along with them a very valuable paleoclimate archive is being lost. The loss of these glaciers have an immediate impact on people in these regions and their ability to produce hydroelectric power, crop irrigation, and for municipal water supplies. It also impacts tourism. On the case of Kilimanjaro, 20,000 tourists go every year. It's the only mountain we've drilled that has its own international airport at the base, which is a big advantage for drilling. But the government is concerned about how many tourists will come to this mountain when the ice is gone. It is the #1 foreign currency earner for the government of Tanzania. So it's important in that way. There's a whole number of parameters you can measure on ice cores. It's very much an interdisciplinary effort. And these are the ones that we measure at Ohio State. And I'm going to show you, this is one of our recent drilling projects on the summit of Kelkaya. 2003, we had the opportunity to go back with the new technology where we could actually bring out frozen ice core. 1983, we brought out 6,000 bottled water samples. And this record turns out to be quite remarkable. Again, Kelkaya is a fantastic ice cap. You can see the drill site up here. And we drilled 2 cores to bedrock. The deepest is 168 meters. And if you look carefully, you can see those annual layers. So it's an annual history. And this record goes back to 200 BC with an annual resolution in the tropics. And to give you an idea of how that record is developed, this is just sections of ice. These are the annual dry season dust layers. And you can see how they're getting compressed as you go deeper in the core. But the thing that really struck us was the reproducibility of the isotopes. These bottles, one set of these bottles were analyzed from the 83 core in Willy Dansgaard's lab in Denmark. The other was in Mincy Storyver's lab up at the University of Washington. And we've come along, and this time we brought out frozen ice core because we have that technology. And this is the overlap in red with from the ice core from 2003 with that drilled back in 1983. And if you take it back 500 years, first of all, the dating was right on for the last 500 years when we did initial work some 20 years ago, but the reproducibility. And so the real limit here is our ability to interpret what those isotopes are telling us. It's a very precise archive of the past. And it also raises some concerns, because if you take the isotopes, these type of isotopes from 3 cores that we've drilled south of the equator in the tropics, and 3 from north of the equator over in Tibet, and you look at the decadal isotope variations from for the last 2,000 years, and you come forward in time, you see very small changes taking place. You can see the medieval warm period here. You can see the cooling during the Little Ice Age. But what really stands out is the enrichments in the last 50 years in these areas. And it looks very much like the Jones and Mann curve, global curve, based on a lot of different proxy records for the Earth. So it would suggest that there's something very unusual going on. The other thing you can do, because you have these annual layers, you can look at what's happened to accumulation. Because accumulation and temperature are the main drivers for these glaciers. And if you look at the decadal precipitation from 1600 to the present, you can see it was wet in this period of the Little Ice Age. The end of the Little Ice Age was dry in these low latitude glaciers. And then by the time you get into the 20th century, it's wetter than average. So all things being equal, the glaciers should be growing and not shrinking as we see them in today's world. So things that on evidence seem probable, glaciers, especially tropical glaciers, I believe to be our canaries in the coal mine for the climate system, because they're integrating lots of different things and they're all giving the same message. And I think the reason these glaciers are retreating at the beginning of the 21st century is increasing temperatures around the world. How do you put this retreat story into even a longer time perspective? And this is something that's just developing. But this is a quote from Sir Ernest Shackleton. He was talking about his ship, the Endurance, that got caught in the ice. But what the ice gets, the ice keeps. But it's true for anything that's in the ice. And we have been amazed as ice caps like the Quelccaya ice cap retreats. These new lakes are forming all around the ice cap. There's new areas being exposed. And as the ice retreats, and give you an idea of the scale, this is where that lake in the previous slide was. 1977, there's no lake. But by 2002, this is the back side of the lake. You can see a person here for scale. But what we found were plants, wetland plants coming out underneath. You can see a deposit here, and if you look a little closer, it's about 2 meters across. What's unusual is it's no woody tissue. These are wetland plants, and there are 3 species in this collection. The dominant species is the Stichia muscoides. This is what the plant looks like, and this is what it looks like in the modern world. And then we had 4 AMS dates at Lawrence Livermore and 2 at Woods Hole, and the plant dates about 5,200 years before present. Now that plant tells us that, number one, it had to be warmer in the past for the plant to be growing there. It also tells us, because it's a soft tissue plant, that it had to be captured very quickly to be preserved. They've actually been able to do DNA on this plant. In 2004, we went back in a different valley, 3 kilometers away, and on this peninsula we collected rooted, soft-bodied plants, and we did 3 collections. And 2 of those collections from here date 4,600 to about 5,000 years before present. And if you look around this period of time around the world, other things have been coming out of the ice, like Utsi, the Iceman. He dates 5,200 years in age. And again, he's a biological specimen, perfectly preserved. And so whatever captured him soon after his death had to be very abrupt. And I could show you records from all these different places, from trees from Ireland to England, to pollen records, but these are all well-dated records with timing showing this very abrupt event 5,200 years ago. And what it tells you, this is in the warm period we're living in, and it tells us that the climate system is sensitive, capable of very abrupt changes over very short periods of time. The other thing that was striking on this collection, the 3rd plant collection, actually came from over here, where this ice field is retreating. And this one is, again, there are 3 different species in the collection. This is one of them. It's a moss. This is what it looks like. You can look at the cell structures in this moss, perfectly preserved. And Leon Blanca and her husband, Ken Young, down at University of Texas at Austin, have spent their life collecting plants in the Andes, and they do the identification of the plants for us. And this is a plant from the Colombia in the Andes that has the same cell structure, but it's the preservation here that's remarkable. And this plant, the collection comes from 5,000 meters in the Andes, and it now doesn't grow above 4,600 meters in the Andes. What's really striking about this plant collection is the age. It's over 48,000 years from Woods Hole, and greater than 55,500 years from Lawrence Livermore. It's carbon dead. And you ask the question, well, how can you have a soft-bodied plant preserved in this fashion, to this degree, unless it's been covered by ice for over 55,000 years? If that's the case, then it's being exposed in today's world is certainly significant in this valley in the Andes of Peru about the current warming that is taking place. But I think what can be done here can be done in other parts around the world. So let me conclude. with these conclusions. The mountain glaciers are disappearing, and along with them, we're losing a very valuable archive of our past. A lot of people say that you make these arguments because you want to increase your funding. It's not true. I mean, it doesn't really matter why it's getting warmer. The glaciers are disappearing, and you're losing the archive. And you could stop with the argument right there as to why you should be recovering these records. The loss of glaciers, and especially those located in the tropics, known for its temperature uniformity, are the canaries in the coal mine for the Earth's system. Our best evidence for the current loss of tropical glaciers is mainly due to rising temperatures, and they are higher in many areas than they have been in more than 5,000 years, and certainly in this one valley on the Quelccaya ice cap, it seems in over 50,000 years. Glaciers operate on thresholds, and as such, they are extremely sensitive to global climate change. So thank you very much, and I appreciate your attention.